How's it going, everyone? I'll give everyone a few more minutes to get here. Well, actually, it's 2, so I'll probably just start it off. Thanks everyone for coming today. I know this is not a required lecture. None of this is going to be on the final. This is purely out of your own self-interest. So I appreciate you showing up, and hopefully I'll be able to show you something interesting today. Right, so I'm David, I'm the TA for this class, and I'm going to be giving a guest lecture today on the current topics in additive manufacturing. I'm a PhD candidate in John Pokorski's lab in the nanoengineering department. So just to start things off, we got to ask the big question here is why do we care about 3D printing, right? What's so great about it? What can we do with it that we can't do with other manufacturing techniques, right? Well, the biggest thing that you can do with 3D printing is you can create anisotropic material properties, right? You can create structures with strength to weight ratios and densities that are different from that of the bulk material, right? So you look here at these honeycomb patterns and these infill densities. You can digitally control the strength and the strength to weight ratio of your final structures, which is something you can't really do with other manufacturing techniques. And you can do it just from a program, just from a CAD file. And you can also create geometries that you really either would be incredibly time consuming or downright impossible with other manufacturing techniques, like these hip replacement implants. These are made with a randomized sintered titanium powder. And there's no way you could fabricate this using conventional machining. And what this allows you to do is when these things are implanted, it allows your bone to kind of graft onto the titanium in a much stronger way than with a non-randomized or something that doesn't have as much surface area. So if you were to get a hip replacement, you would want to get a 3D printed one because they're going to be the most secure because they have this geometry, right? So I'll kind of start off with a question to all of you. Does anyone know what this is? Just go ahead and speak up or raise your hand. Who wants to take a guess what this thing is? Oh, we got a chat. Yep, somebody got it already. Yeah, so this is the injector plate for the F1 engine on Saturn V. Yeah, so this is one of the most complex structures that anyone has ever machined. This thing was made out of Inconel and oxygen-free copper, which are two of the hardest materials to machine. And around this thing, you've got integrated cooling channels, and this thing has to take, all 1.5 million pounds of thrust pretty much on that plate, and you have to mix the fuel and oxidizer. There's little channels in there and little rivulets, and every one of these was different, right? These were all machined by hand by expert machinists back in the 60s, right? And because they were all machined by hand, there were little differences in each one of these injector plates. And so I don't know if any of you have seen the movie Apollo 13, but like right at the beginning of the movie, they say, one of the engines cut out on the Apollo 13, the center engine cut out. That was because this injector plate had a slight, was just slightly different than it was supposed to be. And it caused a combustion instability, and the computer shut the engine down, right? So if the reason that I talk about this is because we can't really replicate this, right? All the blueprints are still there, but all the machining knowledge that went into making these kind of things, that's all like, not trade secrets, but voodoo and black magic and machining, expertise that was never written down. So with 3D printing, though, we could recreate this kind of a structure, right? And we could make them all the same. So we wouldn't have a lot of those combustion instability problems if we were to remake these, right? So that's something to think about, right? We've never made an engine larger than this, mainly because, we haven't been able to replicate this design, right? So first, I'm going to talk about, how additive manufacturing works, the various processes that you might use or be interested in. I'm going to talk a little bit about metal 3D printing, some of the limitations, and then I'm going to get into my current research, right? So, you know, obviously, as I talked about, aerospace is a big application for 3D printing. Um, you know, here, this is a rocket engine, the Vulcan one. This was made by UCSD's own rocket club. UCSD is actually a pioneer in this metal 3D printing of rocket engines. And the reason it's such a good manufacturing technique for these kind of things is you can make extremely complicated geometries, as you can see here. And that allows you to get a lot of cooling in a small space. And you can make it out of materials that are very conducive to rocket engines, like copper, which, again, is hard to machine. It's also good for kind of DoD applications. You can make drones with these very high strength to weight ratio structures. And also, if you need spare parts on like a battlefield, rather than, you know, having to take all the spare parts with you, you can just take a printer and print the thing when it breaks. ARC, this is the company at UCSD that really pioneered the 3D printing of rocket engines, Additive Rocket Corp. Right. So another big application that I'm sure a lot more of you would be interested in is biomedical space. Right. So as I mentioned, these hip replacement cones, that was a big improvement. How many of you have seen this artificial heart printing? Show of hands. Has anyone seen that paper? Well, I think this was out of Tel Aviv University or some university in Israel, and they essentially 3D printed a heart using stem cells, and they actually got the heart to be functional. They got it to beat, and they implanted it in a mouse. And I'll explain the method they used to make this heart. But yeah, that was another innovation in 3D printing. Implants, prostheses are also a big area. You can see this kind of structure here. This is called a Voronoi structure. And this is a very conducive geometry of 3D printing because you can get a very high strength to weight ratio with these kind of structures. Also, in the dental space, I don't know how many of you know Invisalign. This is one of the first applications of 3D printing at all. These Invisalign braces are actually made using stereolithography. They take a CT scan of your mouth, and then they, you know, 3D print these braces incrementally closer and closer to the desired, you know, tooth alignment, and that allows you to not have to, you know, have metal braces. So this is a big improvement. It's still a very profitable, you know, thing, but it's made using 3D printing. Another application for 3D printing, which is kind of lesser known, is the electrical side of things. 3D or RF waveguides. These things are incredibly difficult to machine. Just think how would you get an end mill in here to kind of hollow this thing out? Well, it's very difficult. And the kind of alloys you need to make these out of, it's pretty difficult. But with 3D printing, you just, you know, center the thing together with a laser. It's real easy. Conformal antennas, again, very difficult. 6-axis 3D printing is kind of, you know, paved the way in this area. And 3D circuits, you know, that's another cool little application. Kindling. These things are pretty flammable, so that's another interesting thing I did. So how does this thing work? How does 3D printing actually work? Well, you take a CAD file, which is something that's, you know, a parametric model of what you want to make. This is generally an editable format, something you can edit and reshape and retool pretty easily. And then you convert that into kind of like a static model, something that is just the geometry itself. It's not really editable. We call that an STL file. STL stands for stereolithography. This STL file, you can then input this into a slicing software. This was really the big innovation that allowed 3D printing to explode in the last 10 years, was the open source slicing softwares. One of them is called Slicer. The other one is called Cura. Is it Cura? Yeah, I think Cura, Kiss Slicer. There's a bunch of them, but Slicer, SLIC3R, was the big one. And it was an open source version of this software that converts these platform agnostic STL files into layer slices and tool paths, which are specific to the printer, right? And the printer is actually pretty dumb. It's just a little Arduino, essentially, or the industrial equivalent, that reads lines out of this G-code file and does what the file tells it to do, right? So it says, move the head to this position. Okay, move it here, turn the extruder on. All right, that's all it does. And then the object is eventually formed. But all the hard computational work is done by this slicing software. That's really the hard part. And obviously the designing of the model, but that's not really, that's a whole separate issue. The cool thing about this is they all really follow this general model. Every type of additive manufacturing, this holds true for, except one, and that's computed axial lithography. And I'm going to talk about that too. But other than that, every one of these 3D printing processes is layer by layer. Okay, so the most common type of 3D printing, the one that you're generally going to think of or see pictures of when you think of a 3D printer, is fused deposition modeling, right? That's the most common, mainly because it's the cheapest and it's really the most versatile, right? There's three types of printers, generally. You've got your Cartesian, which is, it's a box. It's X, Y, and Z coordinate system. Pretty high precision, pretty compact. I mean, it's a freaking cube. Delta, which is this kind of weird looking, spidery looking guy here. This uses a cylindrical build volume rather than a cubic build volume. Also because each one of the axes is identical, you can get much faster print times, because on this Cartesian model, the Z-axis generally moves slower than the X and Y because you've got to move this whole Z stage up and down. Versus on the Delta, all the axes are the same, so you can print pretty fast. And you can theoretically have you can have a large build volume with any of these, but these Deltas generally use belts rather than lead screws. So you can theoretically have a larger build volume too, because you just extend these poles up a little bit. You don't have to extend the lead screws. And then the last type, which has come about pretty recently, is the conveyor type, right? And this, you actually have an infinite build volume. You can build as long as you want in this Z-axis, but the trade-off here is you're kind of gimbal locking yourself, right? Because if you think about it, your Z-axis is the same, your X-axis is the same, but your Y-axis is kind of shared with the Z-axis. So you're kind of trading off your print geometry in exchange for this infinite build volume. So there's a lot of limitations that come with this, and it's still an ongoing subject of research, but these are becoming more and more available. And these are great for manufacturing, mass producing things, because with one of these guys, after each print, you've got to like remove the thing, take it off, start the new print. With the conveyor type, you can just have it print continuously and it'll just, chuck the things into a bin. So that's really nice, but there are a lot of limitations with that system. So the critical variables that you really want to look at when you're thinking about getting an FDM system or using an FDM system are, what temperature can your system get to? Because that's going to determine your materials portfolio that you can use, right? So most of these FDM printers have hot ends these days, but some of them don't. See here, this one's got a peak heat break. Generally, these are limited to about 240 C. So that's going to limit you to nylon and weaker materials. And then these higher end printers are probably going to have an all metal hot end. Those can theoretically go up to 350, 400 C. And with that, you can print most materials. But some materials that have a high warping, such as ABS, polycarbonate, you really need a heated chamber for those. So that's, another thing to think about. And I'll talk about that a little bit later. The other thing to think about is how fast can these things move, right? So as I said, the Delta printers are a little bit faster, so that's going to enable you to print larger objects in less time. And the last thing, probably the most challenging part of 3D printing, just for anyone, is bed adhesion, right? Getting the prints to stick to the bed throughout the print is very challenging. Generally, you want a bed with a PEI adhesion layer. These Prusas are, the reason everyone gets these Prusas is because they have a very good bed adhesion layer and they have a computer controlled auto leveling. Something like this Delta is going to be very hard to level because the bed leveling is harder because you have a kind of a hemispherical effect from this Delta geometry. And also these glass beds are very difficult to get prints to stick to reliably. So things to think about. So in general, FDM is a very cost-effective method of 3D printing. These things are, you know, you can get one for $200. You can get a good one for about $1,000. You can print all thermoplastics, no thermosets, but pretty much all thermoplastics can be printed. You don't need any special post-processing equipment. You don't need inert atmospheres. You can print things pretty fast generally. Your resolution is going to be fairly limited. You know, you're still going to be able to see the layer lines, and it's going to be a little bit bumpy, but overall, it's good for most applications, right? So that's what a lot of people use. I'm going to talk a little bit about the polymers that people normally print with and the benefits and drawbacks of each, right? So I know this entire course has been about polymer processing and, you know, the math behind the polymers, but now I'm going to talk a little bit about the engineering and material science of selecting a polymer to print with, you know, the practical side of things, right? So here's, you know, common materials that people 3D print with, right? You got your PLA, ABS, and PETG. Those are the three most common materials. And then you get into some more exotic stuff with increasing cost and increasing performance, right? Over here, you've got kind of a table of material properties, right? So the first thing that you want to kind of look at is the tensile strength of the material, right? This is sigma, the tensile strength, and that's measured in megapascals, right? So ABS, PLA, PETG, you know, it's okay. Had a little internet problem here. Let's try that again. All right. Right. So if can everyone see me again? Can everyone see the screen?
Yes.
Okay, sweet. Thank you. Yeah. So as I said, with PLA, if you leave PLA in a hot car, it can deform, right? So that's a big drawback with PLA is it cannot tolerate high temperatures. If you want to build something like an electronics enclosure out of if you want to 3D print an electronics enclosure, you probably don't want to choose PLA if the components inside are getting hot, right? Because you could melt your enclosure, right? So you want to use something like ABS or nylon or PETG. Another thing to think about, you know, some of these polymers are amorphous, right? So ABS, PETG, PC, and PEI are amorphous polymers. They do not exhibit a melting point, but they do exhibit a TG. And some of them are semi-crystalline, right? So PLA, PETT, nylon, these are all semi-crystalline. Good rule of thumb with whether a material is amorphous or semi-crystalline is amorphous materials can be made transparent, generally. Semi-crystalline are generally opaque or cloudy, right? That's a good way to tell. The other thing to note is your printing temperature, TP, is going to be higher than your melting point, right? And the reason that is because we want to be able to push that plastic through the extruder at higher speeds. And the higher you increase that temperature, the lower the viscosity is going to be. Another thing to keep in mind is increasing your printing temperature is also going to increase your layer adhesion, right? Because you're kind of, when you have that hot layer of polymer, touching that cold layer of polymer, it's going to bring the temperature up and it's going to enable that sintering a little bit better. All right, so moving on. So yeah, as I said, PLA, general purpose filament, it's all pretty good. It's also kind of biodegradable because you've got this oxygen atom here in the backbone that's going to enable the polymer to biodegrade. It's fairly brittle. If you whack it with a hammer, it's probably going to undergo brittle failure. It's going to creep. You can anneal it to have a little bit better properties. You can solvent weld it, kind of, using some pretty nasty solvents. And if you want to fasten two parts together, it's possible, but it's kind of difficult, right? ABS, this is another polymer that's very commonly used in 3D printing. People are kind of moving away from ABS these days because there's some health concerns with it. I've printed with ABS for the past 10 years. You know, I've never had any health problems, but some people are afraid of this thing, mainly because it releases styrene fumes or can release styrene fumes at high temperature. So something to keep in mind, and it's not as it's not biodegradable like PLA. So, but the good part about ABS is it's got much higher impact strength, and it's a much tougher plastic. Right. So if you whack a piece of ABS with a hammer, it may withstand it much better than PLA. It's also got good temperature resistance. If you leave ABS in the car, it's not going to melt. If you use it in an electronics enclosure, it's not going to melt as easily. Very easy to fasten together with glues and solvents, and you can tap it. You can fasten it together pretty easily as well. But the drawback here is bed adhesion is very difficult. This thing has a tendency to warp off the bed, so that has to be controlled. You either need a heated chamber or a high temperature heated bed. The other thing to keep in mind is, well, the other thing that's kind of interesting is a lot of people, when they first print with ABS, they'll try to print Legos because they'll be like, oh, ABS, that's what they make Legos out of. Let me try printing a Lego. You cannot 3D print Legos. Right? I've tried. These things are made to extremely tight tolerances, like micron level. So if you try to 3D print one of these things, either they won't fit or they'll just fit together permanently and you'll never be able to get them apart. But yeah, interesting side note. PETG, this is kind of another common 3D printing plastic. It's very chemically inert. This is what they make soda bottles out of. It's translucent, pretty tough, good temperature resistance. The drawback with PETG is it's very difficult to fasten together because you can't really tap it that easily, and you can't solvent weld it because it is so chemically resistant. But it is pretty easy to print. Bed adhesion is very good. Matter of fact, it's too good. A lot of people will try to print this stuff on a PEI bed, and if you try to print PETG on PEI without a removal layer, it will rip your bed up. So yeah, this stuff adheres very tightly. The other thing a lot of people ask is what's the difference between PET and PETG? Well, this is the structure for polyethylene terephthalate. You can see this terephthalic moiety here. And this is the structure for PETG. So the difference here is you've got this aliphatic group here. And that what this does is it makes it amorphous, right? It reduces the tendency of PET to crystallize, right? And causes it to become a more amorphous structure, right? Yeah, so let's say you want to build something more functional. You need a higher performance material. So maybe these past three aren't going to do it for you. You need to move up to something a little bit higher performance. So then you might want to think about printing out of nylon, also known as polyamide. We talked a lot about nylon in this class. Nylon is kind of your entry-level engineering thermoplastic. It's very tough, very impact resistant, very easy to fasten together. You can see here it's commonly used in mechanical fasteners. You can also dye it with clothing dye, which is pretty cool. You just cook up a bath of RIT dye and throw your parts in there, and they come out colored, which is pretty cool. The difficulties with printing nylon are high temperature. You generally 245, 250 centigrade to print it. Poor bed adhesion. You need an entirely different type of bed to print nylon. You need a phenolic type bed rather than PEI. It's also very hygroscopic. You have to keep your filament in a dry box when you're printing it. You can't just leave it out in the air. You have to like put desiccator in there, and it's a pain in the butt. Also, your parts absorb water too, so you got to yeah. There's a lot to say about this, but if you need a higher performance material, nylon's a good choice, right? So then we kind of go up the scale again to polycarbonate. A lot of people will start out and try to print polycarbonate because they're like, oh, polycarbonate, this is the best. Let's print something out of polycarbonate. The problem here is printed parts out of polycarbonate are not nearly as strong as cast or machined parts out of polycarbonate. And I'll talk about that a little bit later. When you 3D print this stuff, it significantly reduces the mechanical properties. It's not going to be fully transparent because you've got these layer lines. But overall, it is a pretty strong engineering plastic, right? You can get some pretty strong parts out of it. It's got similar properties to ABS, right? It's easy to fasten together, easy to solvent weld, good heat resistance, obviously. But you have a lot of bed adhesion issues, similar to ABS. And generally, you need a heated chamber, right, to prevent warping. It's also pretty hydroscopic as well. Finally, if you have a very specialized application and a very expensive printer, you can print something like PEEK, right? This is generally considered the best engineering thermoplastic. Obviously, there's ones that are better, but this is the best commercially available one. Very expensive. A spool of PLA might cost you 20 bucks. A spool of PEEK might cost you 500 bucks. So there's a lot of expense, but it is biocompatible, vacuum rated, high strength, etc. Right. So now I'm going to talk a little bit about the different additive manufacturing processes, and there's a lot of them. I'm going to go through them pretty quickly, but I'm going to try and cover the main points. Right. So if we're talking about polymer additive manufacturing, these things generally fall into three categories: extrude things, fuse it together, or use light to selectively cure it, right? So continuous fiber fabrication, this is a pretty similar technique to FDM. It's pretty much the same idea. You've got your heated hot end and you extrude things out. The only difference here is you're also kind of putting this continuous Kevlar or carbon fiber filament into your print, and that dramatically improves the strength, right? So you can get, with this method, you can get parts that are comparable to aluminum in terms of mechanical strength without any post-processing. Yeah, pretty much the same method as FDM. It's more expensive, same kind of resolution limitations, but you don't need any processing, post-processing or entered atmosphere or any of that. Let's say you want to make a more complex geometry, right? So if you want to make things that are really complex, you might have to look at something like SLS, right? SLS has a lot less geometric limitations than FDM. FDM, you're limited by overhangs and resolution and all this stuff. SLS, not as much overhang problems. And you can get higher resolution out of it generally, higher performance materials because you've got a laser, right? It's not, you don't have to squirt it through a hot end. You can make the temperature as high as you want with that laser. So you can print on nylon, PC, PEEK. And because you're sintering it, generally the parts are more isotropic, right? You don't have these anisotropic material properties with FDM. With FDM, obviously your parts are going to be less strong in the Z dimension than in the X and Y. With SLS, you really don't have as much of that problem. But these are very expensive systems, right? This is not really something you can have in your lab, maybe really fancy labs, but generally this is something you would send out for, right? It's got to have an inert gas system, powder recovery. You know, you don't want to be breathing this stuff in. You got to wear like a hood and mask. MJF, this is kind of HP's proprietary answer to SLS. Really, it's pretty much the same thing. You've got the same kind of limitations. It's a really expensive machine. The only difference here is it prints stuff faster, right? Because you've got a one-dimensional deposition path. It's like an inkjet cartridge rather than like a laser, like a point scanning back and forth. So you're going to be able to print parts a little bit faster, but really the same kind of geometric limitations, cost, etc. Also, your materials are a little bit more limited with MJF. So now we get into the kind of photopolymer-based 3D printing, and these are kind of interesting, right? Because it's a completely different method, right? So the very first 3D printing technology that was ever developed was stereolithography, SLA, right? Don't quote me on that. There might have been some early crazy stuff, but this is the first one that people really, looked at. You can get pretty high details, but it's very slow, right? Because similar to FDM, you've got this laser scanning back and forth, but instead of FDM you've got a point that's squirting material out as fast as you can. This laser has a limited speed, and it's limited by the dose response of your chemical precursors, right? And also, your spot size is very small. Generally, the spot size is 140 microns. And that's really as small as you can make it with the laser, because you have kind of blooming effects with these ultraviolet lasers. It's also messy, right? This is not something I would want to have running in my house. An FDM printer, sure, you can run that thing in your bedroom. It's a little bit noisy. You can run it overnight, you know, kind of a fire hazard, but not really a big deal. One of these things, you've got this nasty chemical resin. After the parts come out, they're all sticky, and you got to have gloves. You got to clean it with isopropyl, and it's, you know, it's a mess, right? So it's not something you want to do, not something everybody's going to want in their home. Right? The materials tend to be a little bit weaker than FDM. It's going to be thermosets versus thermoplastics, right? But they also can handle a little bit higher temperatures generally because the thermoset plastic, they're highly cross-linked. So that may be good or bad depending on what application you're looking at, right? Speed is pretty low compared to an FDM. Cost, with SLA, it's a little bit more expensive just because a lot of people don't use this technology anymore. So kind of the afterthought to SLA was, all right, rather than using a 0-dimensional point scanning back and forth, why don't we use a 2-dimensional, you know, matrix of light? That way, you know, we can speed this thing up dramatically. And so that's kind of the idea behind DLP, or modified or mask SLA, right? These are very cheap these days. You can pick one of these things up for about $300 off Amazon. Same kind of limitations. Your resolution is a little bit better with this DLP method. It can be a lot better if you use lenses to kind of focus things down. Xiao Chen's group does that a lot. But yeah, there's a lot of advantages here, mainly the speed, right? The only downside here is, similar to SLA, your speed is not necessarily limited by the light scanning, but every time you make a layer, that layer adheres to the bottom of the resin tank. So you have to lift it off and then come back down for the next layer, lift off. So this lifting actually takes a lot of time over the course of your print. You know, the layer might take 2 seconds to cure, but the lift and, you know, retract might take 10 or 15 seconds. So most of your time is spent up and down. So the answer to that is clip, right? Some of you may have heard of this as carbon 3D, right? And so this, they use a different material for this window, right? In DLP, they use FEP, fluorinated ethylene propylene, FEP. It's a type of Teflon. And that prevents the thing from sticking, but you still got to do this up and down. With clip, they use a different material here that allows oxygen to penetrate a little bit through this window. And they use a material, they use a resin where the photopolymerization is inhibited by oxygen. So it creates this dead zone effect, and that prevents the part from sticking to the bottom of the resin tank. So you can print continuously, just raising the build plate up as you change that light pattern. And this allows you to print things very fast and with much higher resolution because you don't have this Z-stepping issue. So we actually have a video here in case some of you haven't seen it. Come on, let's see if this will work. All right, so this is 7x speed of the carbon 3D process. With DLP printing, a part like this could take a day. With with SLA printing, this will probably take a day. DLP probably 8 to 12 hours. With clip, you can print it in a couple minutes, right? You can see how fast that thing's moving. Again, 7x speed, so it's a little bit slower than this, but still, you know, there's none of this up and down motion. So that was a big innovation. The thing with Clip Carbon 3D is it's still a patented process. Carbon 3D owns all the IP, so you're not going to see these things in labs for a while because you cannot buy them. They only lease them. I think it's like $40,000 a year to lease one of these things, and the materials are awfully expensive. You can only use their materials. Yeah, it's a useful innovation, right? So one step further past Clip was, all right, what if we just get rid of layers altogether and just use a hologram, right? So that's kind of the idea behind computed axial lithography. And this is a project that one of my collaborators is working on. You guys may have seen this on some social media sites, the Star Trek replicator. Let me show you a video of this stuff. So this is pretty cool too. So this is the only type of 3D printing that, this is the only type of 3D printing that does not use layers. It's a layerless process. So this is real time. This is not sped up at all. What they've got is they've got a vat of material and they're projecting light patterns onto it as the vial spins. And rather than printing something layer by layer, there's a dose response to these photopolymers. And what they're doing is they're selectively irradiating this vial with different patterns so that the geometry they want all reaches this critical dose at the same time. And so it all photopolymerizes all at once. And this takes about 30 seconds. You can see the thing appearing right there. And you can get pretty complex geometries with this. And the print times are very, very fast, under 30 seconds, because really it's all polymerizing all at once. Right, so not going to get into the math behind how this works, but essentially you're taking a 3D model and you're doing some complicated, Fourier transform type stuff.
Hey, David.
Yeah.
For that last one, were they just using like the same wavelength of light the whole time?
For the video I just showed?
Yeah.
Yep. Yeah, that's all just UV light.
Wow.
Yeah, there's no 2 photon stuff going on here.
Okay, cool.
There are, right now, one of my projects is we're working on making this CAL process multi-material. So you can use 2 wavelengths of light and, have different materials polymerize, but that's still in R&D. But as I said, this is very fast, highly scalable, doesn't use layers at all. It's pretty cool, right? Yes, that was the Star Trek replicator thing. This was published in Science, etc. Okay, so then, yeah, I think going back to the two photon thing. So 2 photon polymerization is, I wouldn't really, I mean, it is photopolymerization based, but it's kind of a weird thing. And essentially the idea here is you can make really teeny tiny structures. If you've ever seen any of these, news articles where we made the world's smallest Star Trek, Enterprise, or we made the world's smallest race car, this is generally the method they used to make those things, right? And the way this works is you have a femtosecond infrared laser. This is like $1 million laser. And you take this thing and you focus it down, and only at the focal point does this light reach sufficient energy to photopolymerize the resin, and it doesn't polymerize anywhere else, right? So when you use a UV laser, all throughout this build volume, you're going to be exceeding that polymerization threshold. And so this whole green section is going to polymerize. But with IR, with this femtosecond infrared laser, only the focal point is going to polymerize. And so this volume is much, much smaller, and you can get much, much more precise prints. But this thing takes forever, right? You got to charge the laser up and fire the thing. And each build volume is like a couple nanometers in size. So these things take a long time. You're not going to be making, a tree with 2 photon polymerization because, you're building this thing up, micron by micron. But you can make, fairly complex structures at the microscale with this. So it's an interesting method. And obviously pretty expensive because you got a femtosecond laser. Those things aren't cheap. Yeah. the last method that I want to talk about is the polyjet, right? So this thing's been around for a while, and this is kind of, you know, one step in between SLA and DLP, right? If you have SLA with a zero-dimensional deposition path, which is a point, and DLP with a two-dimensional deposition path, which is a, you know, matrix. What if you had a one-dimensional deposition path, like a line, like a inkjet cartridge, right? So that's the idea here. And the advantage to using this is it's very easy to do multi-material with this, because just like an inkjet cartridge, you can have multiple colors being, you know, coming out at once. And you can also have very high resolution, because if you've ever seen a printed inkjet page, you can get really, really small details with inkjet. And that's the idea. You're just using a photopolymer rather than ink. And you can do multi-materials. This is completely printed with PolyJet. This toothbrush, transparent materials, pretty easy. Transparent, multicolor, multi-material. You can get stuff like this crazy, you know, medical diagram with integrated channels, and you can get crazy structures with this. Pretty expensive, but it's good to know that this exists if you need to make something out of this. So the other method that you'll see in research a lot is direct ink writing, right? So this is a pretty old method, and essentially you're just taking something and squeezing it out of a syringe with pneumatic pressure. And this is, you know, not the greatest resolution as you'd expect. There's a lot of geometric limitations because, you know, you're squeezing the thing out, and every time you squeeze something, it kind of sticks to the layer below it. So you've got to go really slow. And so the parts don't look that great, but you can extrude just about any material that you can put in a syringe. You know, conductive polymers, sure. Silicone, okay. Bio things, yeah. Chocolate, yeah, chocolate's fun. Metal, you know, you can put metal inks and then like fuse them together with a laser, you know, you can do that. Meat, here's a 3D printed steak. So you can put a lot of stuff in a syringe and squirt it out. Resolution's not going to be the greatest. You can see there's some overhang issues here, but the material versatility is really why people use this method. There's a high degree of versatility. So kind of the upgrade to this was a method invented by MIT, which is called rapid liquid printing. And the idea here is just like direct ink writing, you're squeezing something out of a syringe, but you're squeezing it into a vat of gel, and the gel has a similar density, and it's thick enough that the part is just kind of stay there as it prints. So you can print very large objects with this without having to worry about overhang issues or geometric limitations. So your parts are really no longer constrained by gravity, which is very useful. And this was actually the method they used to print that artificial heart, right? So they had you know, you can do big stuff or you can do really small stuff. Because it's in this gel bath, you can get much more complicated geometries, right? So they used a teeny tiny syringe and they squirted one type of stem cells for the main heart chambers and a different type for these veins, it looks like. And yeah, that's how they did it. So metal 3D printing. I'm not going to talk about this too much because this is a polymer class, but this is the area that I worked on mostly. So I'm going to talk about it a little bit. The easiest way to do metal 3D printing is you just take a welder, just a MIG welder, and you put a CNC stage below it, and you just, you know, MIG weld in place. And you can get, you know, decent looking parts out of it, but not the greatest. And you can make really big parts. Like here's this $1 million thing that Lockheed Martin built to make big, looks like I don't know, champagne glasses or something. But you need a lot of post-processing. Inert gas, obviously, because it's a welding process. Not going to talk about this too much, but it is the easiest. Joule printing is kind of the upgrade to this. This is essentially you take a wire, just like a MIG welder, and rather than fully welding it, you're passing it through 2 electrodes, and the Joule heating of that wire fuses the things together. Right? So you can print much faster with this, and you don't necessarily need an inert environment because you're not fully turning the metal into plasma and welding. You're just kind of melting the things together. Binder jetting is probably the most common form of metal 3D printing. If you go to get a part made out of stainless, out of like Shapeways or Sculpteo, this is probably what they're going to give you. And this is really just, you have this metal powder and it's like an inkjet thing. You put a binder down and you put the binder down in the shape of your part, just like MJF, and you build up this part and then you put it into a sintering oven with the metal of interest, and the metal of interest kind of flows into the part, into the voids left by the binder. And you'll also notice that these parts aren't really, there's a lot of porosity in them, so you're not really getting a pure metal. But this is kind of the cheapest way to get a metal 3D printed part. Right, so if you really need pure metal, like structural or mechanical properties of a metal, you really need to go to something like DMLS, which is, you know, kind of the bigger brother to SLS. You've got a really high powered laser and you're sintering the metal powder together. You need an inert atmosphere. And the other thing to consider with metal 3D printing is when you make these parts, the build plate is made out of metal. And so you're like welding your part to your build plate just to begin with. So you got to machine the thing off. So that's, you know, kind of a problem. This is not something that, you know, you can really set up in a lab. This is something you kind of have to have a machine shop for to clean the part up after it's been printed. Right, so you still kind of need conventional machining at the end of the day. Another kind of metal 3D printing thing that's come about recently is selective powder deposition. This is, you're putting down an iron-based powder in a ceramic kind of sand-based outer shell. Then you put this thing in a kiln and you put carbon on top, and the carbon diffuses into the iron to make steel, and it sinters the part together in the process. It's a carburization process. And you can make pretty good geometries out of this, and you don't need an inert atmosphere. You just need a kiln, and that's it. So this is a much cheaper method. And you can actually buy one of these for about $5,000, which is the cheapest metal 3D printer on the market. Yeah, so that's about all I'm going to say about this. And then this is the method that I worked on. I actually invented this method. This is called stereoelectrochemical deposition. And this is, you're using electrochemistry to make your 3D printed part, right? So rather than using a laser or heat or whatnot, this, you've got your build plate and your anode in a metal salt solution. And you can turn on various pixels in your anode, and whichever pixel you turn on, that's where current is going to flow between your anode and cathode, and you're going to get electrodeposition of metal onto your cathode. And so with this method, you can get very, very pure parts because you're essentially electrowinning the metal out of solution. So it's very high purity, very dense metal parts. Really the hard part is making these anode arrays bigger, right? Because this is a MEMS process. You can also print pretty quickly because it's, you know, simultaneous deposition pads. And then there's other weird methods. This thing is like $1 million machine. It like welds foils together with ultrasonics and then machines them away each layer. You can get some crazy structures out of this, multi-material out of metal, crazy cooling channels, right? So there's a lot of options. Ion beam fabrication. This is, you know, you can make stuff on the nanoscale. Yeah, cool stuff there. So, right, so we talked about all these crazy methods, right? There's a lot of methods out there. What can't you do, right? Obviously, you know, there's calibration issues. So as Professor Sy mentioned in the last lecture, the mechanical properties of 3D printed parts are not always going to be the same as cast or machined or forged parts, right? So with plastics, this is especially apparent. Your 3D printed parts in red are going to be much weaker. They're not going to be as tough as injection molded parts. This is pretty much universal. And this is dependent on Z orientation as well. So you'll notice that this smaller curve here is the strength in the Z dimension, and then this higher curve here is the X dimension. So you kind of have the same yield strength, but your toughness is greatly reduced compared to the injection molded parts. So that's a pretty common behavior for 3D printing. But with metals, it's pretty comparable. Aluminum, it's pretty, you're getting a little bit less material properties, but it's pretty darn close. So most of the problems with reduced mechanical properties with metals come from porosity and inclusions, right? Versus with plastic, it's improper sintering and improper annealing, right? Okie dokie. So that's kind of the mechanical side of things. The other limitations come from the geometry, right? Overhangs are a big problem with all 3D printing, except for the ones that don't use, if you're printing in like a gel with rapid liquid printing, or if you're doing a cal system, you're not gonna have to worry about overhangs. But for most of the methods, overhangs are a big problem. Porosity is also pretty big problem, as I mentioned in the last slide. Most materials suffer with porosity. And then economies of scale is the other big limitation, in that if you want to make 1 million parts using conventional manufacturing, you make the tooling die and you do the injection molding and you can pump out parts pretty much indefinitely. With 3D printing, if you want to make 1 million parts faster, you need a ton of machines, and you've got to have a print farm, right? So the economies of scale are not quite as good. The other thing that was a big issue in the past, and I'm not sure if it's been solved completely yet, is process control. As I said, these inclusion issues, a lot of people were very afraid of these in terms of certifying 3D printed parts for use in critical systems. Because with casting or machining, the failure modes of these parts are known pretty well. And even to an extent, composites, we're starting to understand how they fail and how they perform. But with 3D printed parts, it's kind of a question mark. It's kind of a mystery. We don't fully understand how they fail, or it's not a mature enough process. And so people are kind of wary of putting 3D printed parts into safety critical applications because we don't fully understand, how they fail and the kind of defects that can form. Right. What else? Right. So there's a well-established relationship between the volume of the parts, the resolution at which you can print, and the speed at which you can make these parts. Right. And this is just mathematical from geometry. The time it takes to print an object is going to be a function of the volume of the object, the resolution you're printing at, and the number of simultaneous deposition paths. And it's going to be accelerated by the speed at which you're moving these deposition heads across your part. And you can rearrange this equation into a logarithmic, and you can plot it on this path of known printing technologies, and they form these pretty well-defined lines, right? And you're essentially just increasing the size of your machine or decreasing it along these lines. And then if you use more simultaneous tool paths, like here's a 0D, there's 1D, 2D, 3D, you can, move the whole line up, right? But eventually, you're still limited to these lines, right? We really want to be up here, right? With high material deposition rate and high resolution, right? But we're never going to get there because, you can't go more than 3D, right? You can't have more dimensions than 3. And adding more simultaneous deposition paths becomes extremely expensive at some point because those are all redundant parallel systems, right? So if you really want to print big parts with high resolution, we need a different paradigm, right? So the way to kind of circumvent this system is either to print something that kind of self-expands, or print something that self-replicates, right? Because then you go to a completely different paradigm. And the time to print an object is no longer limited by your simultaneous deposition paths, but the speed at which your systems self-replicate. Right? So the overarching name for this kind of field is engineered living materials and molecular foundries, right? This is kind of the goal of nanotechnology, is to be able to make physical objects from the ground up, physical structures or molecular structures. And economies of scale do apply to engineered living materials. So one of the big problems with 3D printing is economies of scale suck. With engineered living materials, they're great because you just have a farm. You just, farm the things, right? Because they're self-replicating. So 3D printing from the bottom up, that's really the goal here. Where was I going to go with this? Right. So yeah, this is kind of the field that I'm looking at. My personal background, I'm kind of switch gears here and talk about my own personal research. Before I do this, are there any questions about the 3D printing technologies or materials that I covered?
Yeah, I have a quick question.
Yeah.
So, like, instead of building one layer at a time, have people tried removing one layer at a time? Because that's one way in which we can, have the advantages of casting and the accuracy of 3D printing into a single process.
You mean like conventional machining? Just like milling?
Yeah, but well, not like machining, but rather when you, like, for example, in photolithography, if of the chips, we use like either a positive resist or a negative resist. So in a negative resist, wherever we shine the light, there the material gets degraded and then we can wash it off. So like we can have like a part which is cast off as a solid, but then we can remove layer upon layer using a negative resist method.
I see. I'm sure people have tried it. I think the big problem with that is you're going to run into geometric limitations from the previous layers, right? Just like with machining, right? If you've got a layer, if you've got multiple layers and you're going to remove only part of the stuff from this top layer, your next layer, you're not going to be able to get to all the parts of that layer underneath because there's going to be stuff left on the top, right?
I see. Okay, cool.
I mean, I'm sure there's work to be done there. It's just, yeah, there's some limitations with every manufacturing method.
I see.
Cool. All right. So I'll talk a little bit about my personal background and current research, and then we can do more questions at the end if people have them. All right. So my personal background, I did aerospace engineering at UCLA. Worked on solid rocket engines, which was pretty cool. I got to make one of the first restartable solid rocket engines. I went in the Air Force for 4 years. I was an officer there. I actually founded a company to do this stereoelectrochemical deposition. When I was in the Air Force, I invented this electrochemical 3D printing thing, got out, founded this company. Then I worked at Cymer, and then I started my PhD at UCSD. And my work at UCSD is mainly focused on polymer material science and engineering. Right? So cool pictures of me in the Air Force, got to fly some cool things, work at some cool places. This is some of the stuff I did at Fabricate Labs. This is kind of a video of the part of the electrochemical printing process. This is an early prototype. You can see here the cathode moving up and down, and then it's forming this spiral out of copper. Right? So this is a very early prototype. This was kind of the more advanced MEMS device where it's got, I think, probably 2 million individual anodes that you can turn on and off with very high current, and you can make these crazy structures, right? This is cool patents, right? So my current research, or one of my current research topics, is the idea that, could we make something using a small printer and then expand it on site, right? So NASA came up with the idea that you could use these Voronoi structures to make very strong, versatile habitats. The Bigelow Aerospace actually used an expanding structure module for the International Space Station. So they sent this thing up. It was like, I don't know, this thing should be playing, but they sent it up. It was kind of like packaged in a cylinder. Then they released the bands and inflated it with oxygen, and you can make a big habitat module, and they mounted this thing on the ISS, and it's still there. And then other people have discussed the idea of using 3D printing to make, habitats. Right. So we kind of got to thinking about how could we use expandable technologies in the context of 3D printing. Right. So there have been some prior art in this area. People have made these photopolymers and made these blowing agents such that you can put the two together, cure it lightly, and then expand it, and then cure it fully. And there was one paper that got 44% expansion. And we want to do something a little bit cooler, right? So we kind of had the idea of what if we could like print a chair and then like heat it up and then actually like sit on it. So that would be cool. Or what if we could print like a wind turbine blade, like in a small form, and then like drive it out somewhere and expand it to a big, huge wind turbine on site, because the way these are normally transported is you make them in a factory and then transport these huge blades like over the highways, thousands of miles to where they're going to be installed, and it's a real pain. So that was kind of the idea behind this stuff. So actually succeeded in this project, which is kind of a miracle. Basically consisted of trying a lot and erroring a lot. The idea here is you can make something on CAD, print the thing, heat it, and it expands, right? And kind of to get the chemical formulation down, that was really the hard part, because there's not a lot of blowing agents that will dissolve in these monomers. And there's not a lot of monomers that will that are thermoplastic that you can 3D print with a photopolymer system. Like, as I said before, most photopolymer-based printing systems are thermoset, right? They're highly cross-linked, and most FDM, thermal-based systems are thermoplastic, right? So we had to find a photopolymer that was thermoplastic-based, which was very difficult, and find one that would dissolve a blowing agent, and find a blowing agent that would, dissolve in this stuff, right? So it was a lot of trial and error. We found one. It was dibutyl dicarbonate, also known as Bakken hydride. Kind of toxic, but it decomposes fully, so it's pretty safe once it's decomposed. And you can get very high expansion ratios out of this. You can get up to like 40 times by volume expansion. You can also control the expansion digitally. So just by changing the layer height or the exposure time, you can change how it expands and how much it expands. You can also change the cell type. You can go from an open cell to a closed cell foam just by changing the print parameters or the chemical composition. Yeah, so there's a lot of work that was done in that area. Mechanical properties. This stuff is pretty similar to styrofoam in terms of mechanical properties. And then I'm going to talk about, the video is actually pretty cool. Mashable actually did a video on this stuff, which I'll show. It was pretty cool. Is this going to play or is this going to be weird? Is there sound? Oh no, where's the sound? Anyway, here's the video. I'm disappointed. There's supposed to be sound here. But yeah, you can see the stuff expanding in the oven. We also made a little boat. And it looks really weird when it expands. It kind of like contorts around and then it like pops back out again. And the boat floats, obviously, because it's made out of foam, made a wind turbine that generated a little bit of electricity, very lightweight, these things, it's basically styrofoam. And yeah, we made a bunch of different weird shapes out of this and did a bunch of expansions. So pretty cool.
I have a quick question.
Yeah, of course.
So, like, for example, the wind turbine you talked about earlier, how would you, I guess, get it to expand that way? Because, like, it looks like these are, like, smaller objects, and you're able to put them in, like, an oven, like you said, or something. So, like, how would you put all the heat onto something like a wind turbine to get it to that big?
Yes, that's a good question. That's kind of we haven't really gone that far yet in terms of expanding this big stuff.
Yeah.
You could use a larger oven, obviously, or, you could use something like sunlight. or you could use like RF. You could put a carbon powder um, in your resin, and then use an RF, RF energy to heat it isotropically. Yeah, so there's a number of ways to get the heat in.
That was a really cool video, though.
Yeah, thanks. Yeah, I wish the sound would have worked, but the sound, you can look it up on YouTube. It's pretty cool. Yeah, and acknowledgements. These are all the people that helped me do this research. Obviously, Dr. Kai for inviting me here. But yeah, any other questions about 3D printing or foams or just in general?
Is that what you're still working on right now? The expanding method?
Yeah, that's probably
Okay.
one of my main projects. I'm working on making it stronger, like more higher mechanical properties, because this stuff it's not that strong. It's like here, this dotted line here is where styrofoam is at. So the density is about the same, but it's significantly weaker in styrofoam. So we're trying to make it a little bit stronger. Yep. Then I'm also working. Yeah, go ahead.
Sorry, I also had a question about like 3D printing like larger structures. What's like the big difference between the smaller 3D printers and the bigger ones that build like houses or something?
Yeah, it's a great question. So like right now, the kind of the ones that make houses are like concrete 3D printers. That's like a kind of a variation of direct ink writing, right? It's just, you've got a concrete pump, and it, hydraulically pumps the concrete up to a, syringe, essentially. It's a big syringe, and just squirts it out in these rapid liquid, or let me find the method. It's essentially just a variation of this. Wow, that's a lot of crap. Yeah, it's just a variation of that. But the ones that I worked on were actually like photopolymer. So it's this method. So you can print the stuff much faster, not only because it's smaller, to begin with, but also the printing, goes faster.
And how come, like, for example, the house 3D printers, why haven't those been adopted? Are they like too expensive or something? Like, I figured, especially with like the homeless problem we have here in California, and even across the US, like these should just be easily adopted and just, put on autopilot and just create housing structures and, little cities at this point.
I wish it was that simple. Well, scientifically, it is that simple. You could just set up a thing and make these things. But I think the homeless problem is more of a political problem than a scientific problem.
Okay.
But in terms of like actually what is preventing the concrete printers from widespread adoption, I think that's more of just, it's probably going to get there, right? They're already kind of doing it in China, and there's some pilot studies in the US where they're just printing houses. But really the hard part with printing the house is not printing the exterior structure. It's putting all the amenities in there that you really need to live, right? You need a plumbing system, you need a sewer system, you need an electrical system, and, it's a lot. It's probably the same amount of work to install those secondary systems in a 3D printed house versus a regular house, right? And that's kind of the time consuming part. It's not building the walls, it's putting all the, complicated stuff into the house.
Okay.
I don't know. I've never made a house, so.
Yeah.
Anybody else?
Oh, sorry. I have another question.
Yeah, of course.
Are the larger 3D printers being like applied to that project Elon Musk is doing for like building tunnels and stuff? Is that what do you know if that's what he's using to make the tunnels? Like,
the boring company?
yeah, the boring company. Like, you make the I mean, you dig the hole and then you have to build the inner scaffold basically. And do you know if he's using like 3D printers for that, or if 3D printers
So
can be applied to that pretty easily?
that's actually kind of an interesting idea, using 3D printers to make the tunnel sections. I don't know. I don't think they are, because they're pretty big. But the machines they actually use for that are fascinating. They're called TBMs, or tunnel boring machines, and there's only like so many of them in the world. They're huge, huge machines. Let me see if I can pull up, show you one of these. You can look it up on your own, but they're
Machine is not really a 3D printing thing, right?
right. Yeah, it's not a 3D printer at all. It's kind of this huge thing where it's got a giant boring disc on the front, and then it kind of bores the material out and installs these support sections as it bores.
I actually haven't seen that. That's pretty crazy.
Yeah, they're very, very complicated machines. There's actually, like, this is kind of like a structure where people like walk around while these things are going, and they go 24/7, and yeah, they're crazy.
And so you're
Must be
saying that,
inspired by earthworms.
Yeah, it's like a worm.
yeah,
Exactly.
yeah.
It's crazy. Like, when they get done with one of these things, it's more expensive to disassemble it and remove it than to just have it dig itself into a corner. And that's usually how they dispose of these, is they dig the tunnel, and then they just like dig themselves into an offshoot and like brick them in.
And did you
Right.
say that they build the scaffolds as it's digging through?
Yep.
Oh, okay.
See if I can find a video. I mean, here's a picture of the scaffolds, but yeah, they kind of have these like hydraulic things, and they like push the scaffolds into the cavity after they drill it out. It's all like an automated process. But yeah, wish there was, maybe this thing shows it. Yeah, so it's like you've got it like drills it out, and then there's like a conveyor belt that takes the scaffold, and there's like a hydraulic thing that pushes it into place, and then back here you see all the scaffolds put into place, and then they have like rams that like push them in. But yeah, I mean, that is a possible application for 3D printing, is if you could like take this, earth material and like put it into a 3D printer back here, and like print the freaking, support things out of the earth. That would be crazy, man.
That would be really cool.
Yeah, like a self-contained system. But yeah, I don't think that's what they do. I think they just transport the things from outside.
Can we use something like that to fill up sinkholes? Because I believe Florida, being one of the most beautiful places, still has a sinkhole issue. And so maybe we can use like a sinkhole itself to 3D print a home inside it, or something like a hobbit hole.
Yeah, I mean, it's not using a 3D printer. Well, yeah, I don't see why not. I mean, well, I suppose it'd be just as easy to kind of like spray concrete or spray foam or something on the outside of that. Although, I mean, a sinkhole, it's probably in pretty weak ground to begin with, so it's probably not somewhere that you'd want to live. So I don't know. I don't know much about sinkholes, but maybe, I don't know.
Also, when it comes to building like massive structures in space itself using 3D printers, like what's the status of the technology there? Like, because, it'd be really cool if we could just build a mega telescope in space using 3D printers that just, move themselves around with their own propulsion systems and whatnot. So do you know like how far along that sort of research is, or application?
Yes, sort of. In terms of building massive structures, I don't think there's been a lot done. A lot of, kind of the massive structure research right now, that could be applicable to space is more along the lines of, let me see if I can look it up. MIT fiber robot. Let me see. There are these things. Okay. So yeah, so MIT developed this thing, and it's like this little robot that kind of like winds a fiberglass filament around itself with photopolymer and then cures the thing. And you can make these like huge, like, you know, kind of like plant-like structures using this method. So that's one thing that could potentially be applicable to space, is you could have, you know, these things kind of start out on a spaceship and then them kind of like, you know, make the superstructure. And you can do this with metal too. Welding. I think there's a bridge in China that was made using a self-propelled welder robot. Oh, I don't know if it's here. Yeah, this guy. So yeah, these are like welding robots that move along the structure that they've welded together. And so this is another technology that could easily be applicable to space, because it's very easy to weld in space. You don't need inert gas to weld. So all the welds are nearly perfect. There's other issues, because electricity works differently in a vacuum than it does in air. So you've got a lot of corona issues, but welding is, you know, easy. You can do welding in space. And so this is another method that people have looked at. But yeah, I mean, there's a lot of these 3D printing-esque methods that are applicable to large scale structures in space. Absolutely.
That's cool. Thank you.
Yeah. I think the only 3D printing that they've done in space so far has been like small stuff, like printing a wrench with FDM, or like, I think they've done some bioprinting in space too, but it's been small. Let me see if I can find it. Yeah, so this was like the first thing that was 3D printed in space, was this little wrench. Yep. So that's about the extent of stuff they've done. I think this was printed out of PEI or PEAK or something, maybe PLA, but yep, kind of looks like PLA. I'd have to look it up, but it's been pretty basic. Nothing really crazy done in space, because the thing about space is, by the time you send stuff to space, it's got to be so well qualified by NASA. NASA is paranoid about fire. Anything that could potentially have a heater in it, it's got to be like massively qualified. These technologies have to be very mature before they get to that point. So there is some cutting edge stuff, but anything that has to do with, you know, welding or fire or heating, it's going to be a pretty lengthy qualification process. Anybody else? Cool. All right. Well, that's all I got. I've got a final review session tomorrow at noon. So if you guys want to come to that, that's available. Otherwise, thanks for coming. Good luck on the final, and hope you learned something cool. So hope you learned something useful here today. Thanks, everyone.
Thank you.